Chapter 5, Part 3, Hydrohalogenation and Markovnikov addition. So the first reaction that we're going to discuss is hydrohalogenation, which is reaction with HX. HX could be hydrochloric acid, hydrobromic acid, or hydroiodic acid. In this reaction, you'll see that an alkene plus a halogen acid forms what we call an alkyl halide. This is an alkyl group that has a halogen substituting one of the carbons. So let's look at how this reaction works. In the beginning of the reaction, the alkene will attack the acid. We just looked at the general mechanism of electrophilic addition in the last video, and we saw that the first step in that example was that the alkene would pick up a proton, right? It's going to be protonated. And in this example, since we're actually looking at the acid and not just H+, we also need to show that this bond breaks, giving those electrons to bromine. So what this gives us is our two carbons, one of them with a bond to hydrogen, so this is the bond I just made. The other one is going to be a carbocation because we took the electrons away from it. And then the other thing that we're going to have is bromide. And this bromine is going to have an extra lone pair now because we just gave it to it, which also makes it negative. So we make our nucleophile in the same step that we react with our acid. Now at this point, we have a positive charge and we have a negative charge. The big rule in organic chemistry is when you have a negative and a positive, the negative attacks the positive. So this gets us to our product, which is that we have our two carbons, we have the hydrogen that we added, and we have the bromine that we added. Now, if you were just drawing your products, there's really no reason that you would need to draw this hydrogen. It's implied. You could leave it completely blank. Another way that you could have drawn this product would be just like this. And then remember, if you're doing this on Achieve, it will tell you if it wants lone pairs or not. And I will also be specific on a quiz or an exam, so you don't have to worry about kind of guessing at that. So this one is really simple because we reacted with ethene. There are only two carbons. We know that the hydrogen ends up on one and the bromine ends up on the other. But the majority of examples just are not going to be that simple. So that brings us to this next idea. What if I have an asymmetric alkene and I react it with hydrobromic acid? Where do I put the hydrogen and where do I put the bromine, right? I have two different possible products. On the next slide, we're going to talk about which one we're going to make and why. Hydrohalogenation and hydration both follow this rule called Markovnikov's rule. That makes them a Markovnikov addition. And the general rule for a Markovnikov addition is that the hydrogen goes to the least substituted carbon. And the reason that it does this is that the carbocation ends up forming on the most substituted, which we know is more stable. The nucleophile attacks the carbocation, and then the nucleophile ends up on the most substituted carbon. So that's just a long way of saying this one. But let's draw out the mechanisms and talk about why in a little more detail. So in the first step of our mechanism, this is where we make our decision. The double bond is going to attack the hydrogen. We break this bond and give those electrons to the bromine. So at this point, there are two things that could occur, although only one of them is actually going to happen. One option is that the hydrogen goes to the most substituted carbon, which puts the carbocation here on the least substituted carbon. The other option is that the hydrogen goes on the least substituted carbon, and that gives us the most substituted carbocation. Now, if you're following along, this one would go to here, this one would go to here, right? All they have to do is react with bromide. Now, thinking back to our rules about carbocation stability, this one is primary and this one is secondary. The more substituted carbon is more stable and therefore will form more easily. So the one on the left either would not form or it would form in smaller amounts, making it the minor product. The one on the right is going to lead to the major product of the reaction. This is going to be the one that forms the majority of the product. So from here, we react with bromide. And we end up with the most substituted product. So this is Markovnikov's rule. You go through the most substituted carbocation and then choose your product. So the other thing that I want to point out is that because you formed a carbocation, you do always have to wonder if you could make a better carbocation. In this particular example, I did not want to add that complication. So let's work some practice problems following the rule of Markovnikov addition. So neither of these will have any carbocation rearrangements, but you will have to decide which is my major product and which carbocation will form. So go ahead and pause and try this for yourself. But if you're not ready to try it for yourself, maybe work the first one with me and then pause and then work on the second one. So following Markovnikov's rule, our first step is that the alkene attacks the proton. Anytime you have a strong acid as a reagent, your first step is going to be to protonate something. That's never going to change as a rule in this course. And that causes this bond to break, giving those electrons to iodine and forming iodide. Now the question is, are we going to put the hydrogen here, let's call this carbon A, or here, carbon B? Let's talk this out loud. If I were to put the hydrogen on carbon A, that would put the carbocation on carbon B, which is a primary carbon. That's not going to be what we want. But if we put the hydrogen on carbon B, we would form the carbocation on carbon A. And that would be a secondary carbocation. That is what we want. So that's what we're going to do. So here is our structure. I'm going to put the hydrogen on the least substituted carbon, which gives me the most substituted carbocation. And then I've also made iodide as a side product here. So the next step is that iodide, which is negatively charged, is going to be attracted to that positive charge. So this is a nucleophilic attack of an electrophile. From there, I end up with my product. Now I am going to omit drawing that extra hydrogen right now because we don't need it. But if you really, really wanted it because you want to keep track of what's going on, you can draw that hydrogen in right there. But you don't need it. So this is the major product that would form in this reaction because we went through the most stable carbocation. Now, if you need to, go ahead and pause and work the second one. Okay, so the first step of this one, just like all the other ones we've done so far, is we have a strong acid and we have something that has electrons. We are going to have to protonate it. So the alkene attacks the hydrogen and we break this bond, giving those electrons to chlorine. This forms a carbocation. Now the question is, where do I want to put my hydrogen? I have the choice of this top carbon or this bottom carbon. Remember, Markovnikov's rule tells us that we put the hydrogen on the least substituted carbon so that we end up with the most substituted carbocation. And then we also have chloride as the side product that we made, and that becomes our nucleophile, which attacks our carbocation and gives us our product. So for this product, we end up with a methyl group and a chlorine on the same carbon. And again, if you wanted to, just to keep track for yourself, the hydrogen is still here, but so are several other hydrogens, right? There was already a hydrogen on this carbon that we didn't have drawn originally. And then there are two hydrogens on every single one of these carbons and 3 hydrogens here, but we do not have to draw them unless CHEM is being picky and tells you that you have to. Now, in our last example for this part, we're going to look at what happens when you do have a carbocation rearrangement in a problem. So in this example, it's going to start just like all the other ones. We have an alkene and we have an acid. The alkene attacks the acid, and we give those electrons to the chlorine. This gives us our carbocation intermediate. The hydrogen goes on the least substituted carbon, and the carbocation ends up on the most substituted. So this is a secondary carbocation, but it's situated next to a quaternary carbon, which has a bunch of little methyl groups on it. This is going to allow for a methyl shift, which puts the methyl group here. Now by doing that, I've restructured my carbon skeleton here, because I've added a methyl group here. My carbocation has shifted here. So this is the molecule that my chloride anion is going to attack. So chloride attacks here, and I end up with my product. Now, sometimes students get a little tempted to kind of memorize organic reactions, and they forget about the process that gets them there. And if you end up deciding like, oh, I can memorize organic chemistry, and you forget about these steps, you're not going to draw this product. You're going to draw something very different. If I had just remembered that the alkene reacts with the hydrochloric acid, hydrogen ends up on the least substituted, chlorine ends up on the most substituted, the structure that I would have drawn would have been this, which is not the same molecule at all and would not get you the credit that you want on an exam. So anytime that you are doing an electrophilic addition to an alkene, at a bare minimum, you don't have to draw out the full mechanism every time. That does take quite a lot of time, and if you're taking an exam or a quiz, time can be a big commodity. But at a bare minimum, draw out the carbocation that you would form. You don't even have to draw the mechanism to get there, but draw that carbocation and ask yourself, can I rearrange this into something better? And if you can, do it, because that's going to get you to the correct answer.